So there are many ways to introduce this topic, and the way I chose for this presentation is to revisit briefly the prover workflow of Stark VMs. So the idea is we have the algebraic execution trace, which we low degree extend, turn that into a Merkle tree, send the Merkle root to the verifier, get an interaction, get a challenge from the verifier, use that challenge to extend the trace, the extended trace. So this gives us new columns and allows us to populate some of the variables of the AIR constraints. And then we evaluate the AIR constraints, giving us a bunch of quotients, and in fact we can sum those quotients using weights also provided by the verifier. At this point we get a single out-of-domain row corresponding to some alpha which lives outside of the trace domain. And then we can perform a deep update and run fri. That is the Stark workflow in a nutshell, and if you didn't catch most of the details, that's totally fine. The relevant points that I want to draw attention to here is that there are two stages, the main and the auxiliary stage. So the main stage, the prover commits to up front. The auxiliary stage, he can only commit to after receiving challenges from the verifier. And so the way I want to introduce the topic of my presentation is by planting a question mark behind this fact that is usually taken for granted. Why are there two stages? Why aren't there less than two stages? Why aren't there more than two stages? So let's start with the first question. In a ZK-VM, we describe the state of a processor as it evolves across time, except the processor needs to fetch instructions from a program. It needs to interact with memory. It takes an input and it takes an output, and all those interactions need to be authenticated as well. Even if you can produce execution traces for these individual units and AIR constraints for those execution traces, you still need to authenticate that communication. How do you do that? Well, the way you do that is through the second stage. You get random challenges from the verifiers, and using the second stage, you actually prove these cross-table arguments. And so this is a first step towards answering the question, why don't we just do one stage? The answer is, we want to link disparate logical units that depend on randomness that comes from the verifier. And in fact, the concrete way in which we do this is we create extra columns, auxiliary columns, that depend on this randomness. And what these columns do is they evaluate step by step some polynomial that depends on the entire green part of the trace. And you can think of every row in this extra column as the next step of some evaluation. And the communication between these two tables is authentic if the columns in their last row agree. And so, depending on the particular relation between the tables that you want to establish, you get a different type of polynomial. So if you want to just look up some elements in a table, then you have a lookup argument, which gives one type of polynomial. If you want to establish that two tables are permutations of each other, then you want a permutation polynomial. And if you want to establish that one table and another table, that there's a sublist, order matters, but you can always skip over rows in your stepwise evaluation, then you use an evaluation polynomial. And so this brings us a step closer to a satisfying answer to the question I raised. So we want to use the equality of polynomials to authenticate the communication between these two tables. But the problem is that the AIR constraints, they don't take polynomials, they take scalars. It's just a circuit. And so what we do is we collapse these polynomials using evaluation in a random point supplied by the verifier. And that is sound because of the Schwarz-Sippel lemma. Okay, so the satisfying answer to the question, why don't we use one stage, is we use elementary polynomial arithmetic to link tables together. And since the AIR constraints do not take polynomials but scalars, we need to collapse those polynomials to scalars using evaluation in a random point supplied by the verifier. All right, with that said, what about more than two stages? It certainly seems that going from one stage to two stages unlocks some power. And so a natural question to ask is, which power is unlocked by going to three stages? And if you take nothing else at all from my talk, take this, the answer is arbitrary polynomial arithmetic, as opposed to scalar arithmetic, which is what the AIR constraints usually authenticate. And so what does that mean in more concrete details? Traditionally, we think of a virtual machine as containing a set of registers, and those registers take values from a finite field F. This is the green picture on the left. But if we can authenticate arbitrary polynomial arithmetic, then these registers can actually take values from the polynomial ring over that field. And then in order to make the AIR still apply, we collapse those polynomials back to scalars using evaluation in a random point supplied by the AIR. But the important point is that you can describe the evolution of your virtual machine as an evolution of a set of polynomials as opposed to the evolution of a set of scalars. And so on the green side, where you don't have any interaction with the verifier, you can already authenticate basic arithmetic, and that's nice. If you use randomness supplied by the verifier, you can add and multiply not just scalars but polynomials too, and you can even commit to polynomials inside of the context of the VM. And you can already do this with the standard construction. What polynomial acceleration gives you, and I'll explain later how to do it, is you get to do polynomial division and remainder checks. You get to do polynomial evaluation queries, and you get degree-bound checks, basically for free. One instruction in every case. One row in the algebraic execution trace in every case. And before I get to the construction, let's look at a few motivating examples. Firstly is big integer arithmetic. The idea is we want to multiply, or rather we want to authenticate the correct multiplication of two integers of 2,000 bits or so. Now, you could split these up into digits and then use the schoolbook multiplication or even Karatsuba multiplication and run through that algorithm, and that's rather costly. The way you use polynomial registers to authenticate this correct multiplication is you construct polynomials that represent these integers, a, b, and c, where c is the product of a and b. These polynomials have to have binary coefficients. Well, I guess you can do some packing, but as a first approximation, it works if these polynomials have coefficients that are all 0 or 1, corresponding to the binary expansions of the integers. And then you calculate the product of those two polynomials, a and b, subtract what you claim is the correct product, and you reduce that modulo x minus 2. Reducing modulo x minus 2 is the same as replacing every occurrence of x by 2, and so this corresponds to sending your polynomial consisting of bit coefficients to an integer with the same bits. It works as long as there is no overflow in your coefficients. And then you just assert that this remainder is 0, because it has to be if and only if you calculated C correctly. And so it only works if there's no overflow, if your coefficients are never larger than P. If they are larger than P, then there's a problem. And so in terms of cost, you do need to spend a linear amount of time constructing A, B, and C. But once you have constructed A, B, and C, you can calculate this remainder in a constant number of steps, and you can assert that it is equal to 0 in one step. And this works independent of the circuit depth. So you can do this again and again and again, and you really only need to construct the inputs to your arithmetic circuit over the integers. All right, a second motivating application is the last round of FRI, before you sample the indices for opening the coefficients, for opening the code words and checking their collinearity checks. At some point, the prover needs to send a code word, and the verifier needs to check that this code word is of low degree. And so traditionally, what I think is the fastest way is for the prover to send both the last code word and the polynomial that interpolates through it. And then the verifier uses Horner evaluation to evaluate the polynomial in a random point, uses barycentric extrapolation to interpolate and then re-evaluate the code word in a random point. And then he checks that those 2 points are the same, and the verifier needs to do T collinearity checks. Using polynomial registers, polynomial acceleration, we can improve on this. The prover only needs to send the polynomial, which, by the way, does need to be represented as a list of coefficients, because that's what the proof consists of. But actually, I'm not sure about that last fact. I think the prover might even get away with not sending that. I need to think about it. The point is, the complexity of the verifier drops. So the verifier does need to construct this polynomial, which takes around linear time. And then he does need to evaluate it T times to get the points for the collinearity checks. And he needs to verify the collinearity checks. But if you compare the second line, the cost of the barycentric extrapolation disappears in favor of T evaluations. And by the way, evaluations of polynomials contained in polynomial registers can be done in one cycle. All right, last application is single instruction, multiple data. Polynomials, you can think of them as vectors, and so it should come as no surprise that when you add two polynomials, you add two vectors of numbers. Very simple. But the same works for multiplication. If you want the Hadamard product, it depends on how you represent the vectors. If you represent them as the evaluation on some domain, then you need to modulo your polynomials by the verifier of that domain. But then you get the Hadamard product of the evaluations on that domain. You get point checks into these vectors through evaluation queries. And once again, evaluation queries take one cycle. And you might also want some kind of aggregate measure. And so, as an example, you want to compute the inner product of two vectors. What you end up doing is you compute their Hadamard product, and then you want to compute the sum. So how do you compute the sum of such a vector? Well, you compute the sum that defines the polynomial a minus s over the size of the domain. And this is a new polynomial that has to satisfy this equation, this polynomial that supposedly sums to 0 has to be describable as the difference between the same polynomial evaluated in x and omega times x. And yes, you do need to construct C again. That takes linear time, but you only need to construct C once, regardless of the number of sum checks that you do. You can do 100 sum checks, sum all the C polynomials, and construct it once. So that's batchable. But once again, constructing these polynomials does take linear time, and that is hinting at one of the open problems that I'm looking to solve. All right, here is a more concrete presentation of the construction. This is an example. I'm sure there are many different ways to achieve this. And I'm afraid this slide is rather overloaded with formulas and notation. It's mostly for the benefit of the recording. So here we go. We have polynomial registers PR1 through PRn. And for every polynomial register, we also need to track their degree somehow. So we have degree tracker 1 through degree tracker n. And then whenever we have a division operation, we also need to store the results, which are the quotient and remainder, along with degree trackers. The purpose of this accumulator polynomial is special, and I'll get to that later. These polynomials are for bookkeeping. You need the degree trackers and their inverses in some cases. And these columns, in fact, don't interface with the state of the VM. They are there for a different type of bookkeeping. So, for example, we have a numerator of degree at most bn, and this means that the degree tracker is x to the power minus bn. And we have a denominator, d, of degree at most bd, which means that the degree tracker is x to the minus bd. We store the result and the quotient similarly. Excuse me, we store the remainder and the quotient similarly. The accumulator polynomial is the only register that represents a polynomial in two variables, x and y. The degree trackers are the inverses, the bookkeeping degree trackers are the inverses of other degree trackers, and which other degree trackers depends on the concrete instruction and which polynomials are actually being combined. And these extra bookkeeping columns represent the evaluation of the accumulator polynomial in beta, where beta is a value supplied by the verifier at the right point in time. And so the idea is we get beta from the verifier and we get alpha from the verifier. And with alpha, x disappears. With beta, y disappears. So whenever we have a y, that becomes beta. Whenever we have an x, that becomes alpha. And so after alpha and y, alpha and beta are known, everything becomes scalar. And so, in order to authenticate a divide, a polynomial long division resulting in both a quotient and a remainder, we have to establish this relation where double slash denotes divide and forget about the remainder, and we have to establish their degree bounds. And the degree bounds are tricky. The equality that the numerator equals denominator times quotient plus remainder, that's trivially encodable as an AIR constraint. But how do we do the degree bounds? Well, what we came up with is using the degree trackers. This is where the accumulator polynomial comes into play. Its purpose is to collect a whole bunch of univariate polynomials in X. Each of them are assigned a unique power of Y. When you evaluate this in beta, replacing Y by beta, what you get is a random linear combination, parameterized by beta, of all those univariate polynomials in X. And so the accumulator polynomial A undergoes a bunch of updates where you multiply its old value by Y and add in a new univariate polynomial. The term that you add looks like this for a degree-bound check on R, right? Because the degree of R is supposed to be less than BR. And so N is the maximal degree. You subtract BR from N, and this gives you a little bit of space. If you multiply the polynomial R and the equation does not check out, you will have a higher degree than is allowed, and this will be caught. Specifically, if R exceeds the bound, then the degree of this term on the right-hand side will be larger than N. And we do the same for Q on the right. And so we've reduced the low degreeness claim of polynomials to low degreeness claims of monomials. These are the degree-bound checkers. The point of this reduction of polynomials to monomials is that we can actually divide monomials cleanly. It's easier to prove that monomials have a bounded degree than polynomials do. And in fact, we can, this is one place where we use the inverse degree trackers. You just multiply the right registers, you get a new polynomial, and you update your accumulator with those monomials. All right. These 5 updates to the accumulator polynomial can be authenticated through a rather complex error constraint, but this is not enough because we still need to establish somehow that after we evaluate A in beta, replacing Y by beta, its degree is low. And that's what the extra bookkeeping columns in the red on the right are for, because they go into FRI. And so this establishes that some polynomial that we hope is equal to the last row of A evaluated in beta has degree less than N, but it still doesn't establish that it corresponds to the last row of this register. And so how do we establish that? We use an out-of-domain sampling point here. Since this value is collapsed using both alpha and beta, we just look at its value in the last row, and then we have A evaluated in alpha and beta. And so that is an out-of-domain evaluation which we can use for a deep update. And since we're integrating this last column, that gives rise to an error constraint. So, using this construction in the context of a Stark modifies the Stark workflow. In particular, we have this extra stage in between the main and auxiliary stages. This is where we already received beta from the verifier, but we did not receive alpha yet. At that point, we can produce the extra bookkeeping columns. These extra bookkeeping columns, they represent segments of a polynomial of degree k times n gives k segments, each one of which are code words. All right, so this construction is nice, but it's not perfect. And one limitation is that you cannot compose polynomials. And that wouldn't be such a big problem because you can still verify that two polynomials correspond to the composition of, or two polynomials composed correspond to another. You can still verify this, but you cannot non-deterministically guess polynomials. That's the second limitation. The efficiency gains come from delegating to the prover outside of the algebraic execution trace work. It shrinks the algebraic execution trace, but you're still always working on the prover side, not on the verifier side. So you cannot benefit from the succinctness that verifiers get in traditional snarks. And so in particular, you need to bind down your polynomials coefficient by coefficient somehow. And that's why I keep reciting it takes linear time to construct these polynomials. And so that gives rise to an open question. And if you're of that mind, please solve this for me. It could take the form of a hash function or of a commitment scheme, but we want some way to verify that a divined polynomial or a non-deterministically guessed polynomial of degree n corresponds to a constant size cryptographic digest. And we want to do this in a number of cycles that is asymptotically less than the number of coefficients. And corresponds uniquely, you do get to use cryptographic hardness assumptions. In fact, I think you need cryptographic hardness assumptions. But the point is, you get to use single instruction, multiple data instructions in the course of verifying this polynomial. So you can think of this as sublinear hashing, sublinear in the input, but assuming that you get single instruction, multiple data instructions. If we can do that, that unlocks much more power than I've described so far. Then we can simulate arbitrary polynomial IOPs on the prover side, thereby shrinking the algebraic execution trace a lot. That's it. Thank you for your attention.
We have time for one question. Perhaps while the next speaker sets up, if he's here.
So in this construction, you use three phases, two separate verifier challenges computed in sequence there. Do you think there is a way to do this while still remaining two phases, or I think that's probably pretty fundamental to the construction? Not to say no, this is, yeah, anyway.
I can't say that I've exhausted the search space, but I did try to reduce the number of stages, and it's infeasible. It seems like you really do need one challenge before the other challenge was sampled. You need to commit in between those two challenges. You need to commit to something.
And that third stage is added is mostly for degree tracking, essentially, or degree guaranteeing low degreeness of the results. Did I understand that correctly?
I didn't catch the question.
The third stage, the red stage, is about making sure that the results are low degree. Did I understand that correctly?
Yes.
Okay.
Correct.
Okay, thank you very much.